There's one example that has some complex splitting. So we were able to, we were looking at that and we left off talking about the fact that those hydrogens, the purple hydrogens next door to the chiral center, this one, and we give the other one a different color, this one, they're not the same. And so that's why you see these two signals down here. All right. And so depending on which one is wedged and which one is dashed, that's going to determine which signal is further downfield or upfield, because the wedge will be closer to oxygen than the one that's on the dash. So let's say for the sake of argument that the red one is on a dash, and then the blue one, I'm sorry, on the wedge, and then the blue one is dashed. All right, so that's those two signals right there are the two distereotopic protons next door to the hydroxyl group. All right. So now let's look at the splitting pattern. And I don't know if you can see this, but let's look at the one that's in blue because the resolution is a little bit better. But there's like 4 lines there, right? But it's not a quartet. So you got 2 lines here, and then you got 2 lines here, and it's not symmetrical. And there's a reason for that. The reason why it's not symmetrical is because this is a complex, one of our many complex. This is a right? It's a complex splitting pattern. And what it looks like, since it's 4 lines, it's actually 2 doublets together. And I'll explain that. So that particular pattern is what we call a doublet of doublets. Right, so it's 2 doublets together. And the reason, all right, we go back up here, and this is the blue proton. It's going to split with the proton that's circled in red, and it's going to split with the one that's highlighted in green. So the N+1 rule, we're going to apply it twice, right? So that signal is going to be split into a 2 doublets, right? So it's going to split here. Different color. So it's going to split there, and it's going to split with that one. So if we apply the N+1 rule, there's going to be 2 for that, and then also it'll be 2 for that. So that's why you see 2 doublets like that. But it's the same signal. It's just split into 2 doublets because of that. What we call on Friday multiple non-equivalents, right? You got multiple protons that are not non-equivalent to one another, and they're splitting each other. All right. Questions about that? Because it's the same, you're going to see the same thing for the red proton. You can see that that's also 4 lines. It's a little, the resolution is bad, but you can see it down here. That's 4 different lines. So that also is I'm just going to abbreviate it, a doublet of doublets. For the same reason, it's going to split with the blue and with the highlighted green proton. All right, questions about that? Any questions? All right, so we know now that this is the spectrum for A. Right? So let's go to the next spectrum and see if we can solve that one. All right, how many signals do we have here?
Five.
5 signals. Okay, good. And we don't have any infrared information. No infrared data. All right. But we can see that it's 5 signals. Which of the molecules did we predict to produce 5 signals up top?
The third one and the last one.
So C and D. So what we need to look for to rule out C or D, these protons right here in D, right? They would show up. Where would they show up? You should have an idea now about the chemical shifts. Where would they show up? What region?
Downfield.
Yes. Further downfield in 3. So these are what we call vanillic protons. We talked about that. It's been a few days, but you got to look back at the chart that was presented. But it's a vanillic proton, so they show up somewhere between 5.5 and 6.5, right? But you don't see that on this spectrum. And then it can't be B, because B we predicted to give at least 6 signals at a minimum, right? So we can rule that out. So it has to be the epoxide, C. It's got to be this one. All right, so now, let's see, let me grab the one that's color coded. Right, so we know that just based on the number of signals, which is a great way to figure out or to determine if you have choices like that. That's a great way to rule out certain spectra and know what spectrum you're dealing with. All right, so we got 5 signals. Let's start with the CH3 on the left, the blue one, right? What should that signal look like? What should it be split into? And where should it show up?
It's going to be a triplet.
Definitely going to be a triplet. And if you look at the spectrum, we only have one triplet. Is that right?
Yes.
Down here at about 0.9. I said 0.8 or 0.9. I need to remember which color highlighted. Yeah, that's the right color. So it'll be this one. And it's integrated for 3 components. Right, so that's another
Sit
clue.
down.
All right. All right, let's go to the purple one, the other CH3. What do you think?
It's a doublet.
It should be a doublet, and we only have one doublet in the spectrum, right? And that's going to be this one. What color is that? Purple. That's going to be this one. Is that right?
Yes.
And the location matters because it's an alkyl type proton. It's a little bit further downfield than the other one, because of its proximity to oxygen in that epoxide, but it's still an alkyl proton, still showing up in the same place, or the same region where it should. All right. Now let's look at the CH2. Let's look at that one. What do you think? Which signal is it?
Would it be where the 2H is? Is it a no?
Right here.
Mm-hmm.
Yeah. You can see from the integration, that's the only carbon in that molecule that has 2 hydrogens on it. But then the other part is the splitting pattern. So you can look here and see 1, 2, 3, 4, 5. It's a pentat. Shouldn't it be a pentat?
Yes, it is.
And it's got 3 neighbors to the left and 1 to the right. So n plus 1, n equals 4, n plus 1 is 5, so it should be a pentat. So I'm going to put that here. It's a pentat at about 1.4 parts per million. And this one was a triplet at 0.9 parts per million. And then this one was a doublet at about, I want to say 1.2. All right, so now we only have left the 2 protons on the epoxide. All right, and they are adjacent to each other. You can see that. So let's take the pink one. What should that, which of those 2 multiplets is going to be that one? And you can tell by the splitting pattern. You should be able to tell by the splitting pattern.
The one on the
Go ahead.
right.
On the right here.
Yes.
Yeah, it should be a quartet. Right, and it's showing up right at 2.5. Right, and then the other proton, this one, what should that be?
The one on the left.
Yeah, it's a pentet, right?
Oh.
You're right that it's the signal on the left, but it's a pentet. And it's going to be, I say, about 2.7. Right? It's this one. It's 5 lines. That's 5 lines, and then this one is 4 lines. Right? So I have a quartet and a pentet. And then you have down here another pentet. Right? What's the difference between the 2? You got 2 pentets that are possible. What's the difference? Why is one further upfield than the other?
One is closer to the oxygen.
Mm-hmm. The one that's the protons that are on carbons that are bound to oxygen, like the ones in the epoxide, those are going to be further downfield. Right? So sometimes you might have a signal with the same splitting pattern, but a different chemical shift, and you need to be able to work through that nuance. Yes, they're both pentets, but one of them is upfield and one of them is downfield. So yeah, so this is the spectrum for C. All right, let's go to any questions about that before we move on to the next one. Right, this one should be a dead giveaway because of the infrared.
So we're working with D. I mean, not D, B.
B.
Mm-hmm.
All right. Why do you say that? You're right. I agree with you.
Because of I see it where the OH group is. We already did A, but I see where the OH group is.
You got a big
Um,
alcohol stretch right here in the infrared. Is that right? That's
yeah.
a dead giveaway. When you see that broad stretch like that, it's a dead giveaway that there's an alcohol present in your molecule. And that's why infrared is so important because you can actually see that OH stretch. All right. Let's go up to the spectrum. How many? Let me pull it from up here. Sorry for all that. All the. We're gonna just paste this down here. We'll walk it down just like we did the other ones. All right. So based on the spectrum, there's no complex splitting. So these chiral centers are undefined, right? I had them defined. I think I drew that in. I'm gonna take that out because they're not. Can I take it out? Oh, I took the image. Never mind. Hold up. Let me see something. I can erase that up here. All right. So you can look at look at the spectrum, right? The protons that are next to the bromine and next to the oxygen are not showing up as complex splitting patterns. So you don't see a doublet or doublets or some other splitting pattern that would be considered complex. So we can just walk this one down. So let's start with the methyl groups, right? Both of those methyl groups should be, where should they be and what should the signal be split into? You can see the integration, right? At downfield, you got two signals that are integrating for 3 hydrogens each. So where should the signals be for those 2 methyl groups? And then what should the splitting pattern be?
So wouldn't it be a triplet?
Mm-hmm.
And then
For both of them, right?
yeah.
Mm-hmm.
And then they would be where the 3H is. But okay, what I'm confused about is like which one is which, because I know last time one was closer to the oxygen, so that's how we
Mm-hmm.
discovered the splitting pattern. But how do you determine this one?
That's a good question. Probably what we'll probably will have to do is a carbon NMR to look at because the carbon where the bromine is attached and the carbon where the oxygen is attached are going to look different. So you can do a carbon, and then based on that, and you can also probably look at the coupling constants, which we don't have if we had the chemical shift, then we could figure out what the J coupling is between the lines in the signal. But let's just say, for the sake of continuity, the CH3 that's on the end where oxygen is, we're going to say that one is more deshielded. So it's going to be the one further downfield. All right. And then the one that's closer to where bromine is, we're going to say that is further. That's going to be the one that's further upfield.
Okay.
Is that fair?
Mm-hmm.
All right. So let's do that. So let's say that this triplet right here is going to be the one on the OH side. And then the other triplet here is going to be on the bromine side. So both of those should be a triplet. And then we'll say that it is at 1 point. Did I screw that up? Yeah, I did screw it up. Sorry. It's supposed to be the opposite. This should be the one on the bromine side. And then the green one is on the oxygen side, like that. All right, so that's going to be a triplet at, let's say, 0.8. And then over here, this is also going to be a triplet, but it's going to be at about 1.1, somewhere in there. So 1.1 parts per million. All right, so we got those two out of the way. Now we have two methylene carbons that we need to look at. Right, so you can see, and they're both in a similar position structurally, right? They both are adjacent to a methyl group on one side, or CH3 on one side, and a methine carbon on the other side. So we're going to apply the same logic. The one that's closer to oxygen, we're going to make it more downfield, and the one close to bromine will be the one further upfield. Let's do that. So which one is going to be the pink set? These colors all starting to blend together. If both signals are integrating for two hydrogens. Would it be this one?
Yes.
Yeah, that's the one that's further upfield. And then the other set, the blue set, we're going to put here. That's the wrong color. All right. So what's the splitting pattern for each?
Five.
All right, so each one of those should be a pentet, right? This one has 4 neighbors, and so does this one. Got 3 on the CH3 to the left for the pink ones, and 1 to the right. All right, so that one is going to be a pentet. And that is at about 1.4. And then the other is going to also be a pentet. And that's going to be at about, I said 1.6. So we only got 2 protons left, and that's these. And you can see now here, the resolution is pretty bad because there's some overlap with the OH proton, but we can still determine what the splitting pattern should be. So what would the splitting pattern be for the, that's the gray color proton that's adjacent to bromine?
It would be 4.
It'll be a quartet. Good. So that should be a quartet. And then this should also be a quartet. Is that right?
Yes, sir.
Yes.
All right. Now the difference is where they're located. So we know now that the oxygen is more electronegative than bromine, right? So that's going to push the signal for that carbonyl proton further downfield. So this one is going to be representative of a proton adjacent to oxygen, and this one will be a proton adjacent to bromine. And if you look closer, you can see that they're both quartets. But the OH proton is overlapping with one of them, right? So you see that's 1, 2, 3, 4 lines, and this is also 1, 2, 3, 4 lines, and it's not complex. If it was a doublet of doublets, the signal wouldn't be symmetrical like that, right? So that's how you can tell the difference between a doublet of doublets and a quartet, is the symmetry in the signal. You see how in this quartet, the two middle lines are higher than the two outside lines? That wouldn't be the case for a doublet or doublets. All right, so that's how you know that chiral centers are undefined, where the bromine and oxygen are. Because if they were actually defined, then you would see complex splitting with those and the distereotopic protons next door to it. But you don't see that. All right, so I'm gonna write that in for here. No chirality for that. So we know that this is the spectrum for B. And we didn't put that in. That's at 3.6. And then this was at 3.5. Man. All right. Any other questions about this one? There's another there's another aspect or another part to the infrared too. This little peak right here that you see is about let me see, it's about right at about 1100, about 1200. That corresponds to a CO single bond. Right, and the reason I'm pointing this out because these are common. Like the CO single bonds somewhere between like 1050 and 1200, somewhere in there, depending on what type of single bond it is. All right, so that's a common stretch that you should know, just like the carbonyl stretch, the alcohol stretch, the alkyl stretch. I don't think we saw any aromatic stretching here, but I know that it's in the there's aromatic stretching in the infrared video that was sent out. All right, so those are stretches you should commit to memory. All right, so now we know that this is D because we've ruled out all the other compounds. And so let's go up to here. Grab it. No, too far. So we can see right with D, we said we predicted 1, 2, 3, 4, 5 signals, and we see 5 signals. All right. And we also said that the alkene protons are going to be non-equivalent. So each one of those is going to be separate. They're not going to be one signal. There'll be 2 signals. And you can see down here in the alkene region, you can actually see that there are 2 signals. Look at where they show up between 6 and 7. So that's typical for alkene protons. And this is just this is blown up, a zoom of that section. So you can see one of them is a doublet. The other one is some weird looking signal. It's actually a complex pattern, like something we haven't seen before. So we're going to talk about that. All right. So let's look at the infrared. You can see a nice carbonyl stretch right here. And that's about 1700 reciprocal centimeters, right? That's going to correspond to your ketone. And then you also have some alkyl stretching down here because of the ring. No, wrong pen. That's carbonyl stretching, alkyl stretching. That's, you expect that. The double bond stretch is probably somewhere in here, right? The alkene stretch is a little less intense than the carbonyl stretch, and sometimes it shows up between about 14 and 1500. So, and depending on how it's substituted, it may be further down. It may be closer to 1600, but the alkene stretch is not as intense as the carbonyl stretch. So let's look at the signals. Let's start here with the pink signal, right? That is adjacent to your carbonyl. Do you expect it to be further downfield or further upfield?
Downfield.
Downfield. All right, so let's look at the choices. We got 3, and it's not going to be down 6 or 7. That's a specific number, a specific chemical shift for protons that are on carbons that are adjacent to sp2 hybridized carbons, like carbonyl carbons and vinyl carbons. All right, so, and all of these are integrated for 2 hydrogens, so you can't tell them apart using the integration. You have to use another piece of information, and that is you need to use the chemical shift data that you know, and you also need to use the splitting pattern. We can use that too. All right. So what do you think for the pink color protons? You can see that it's a triplet. Don't be shy about it. Just, if it's wrong, we're gonna correct it. If it's right, then that's good.
You said that one's gonna be, since it's next to the carbonyl, it's gonna be more downfield, right?
Yes.
So it would be where the that, okay, there's 3 2H's. Where the 2 is that right?
Right here.
Right. Oh no, I wasn't talking about that one, but
yeah, but they all integrate for 2 hydrogens. You following? Like everything is 2 hydrogens. So I was just saying you can't use it just simply the integration. But if you look at the splitting pattern, right, that particular set of protons, what should it be? What's the splitting pattern going to be?
3.
It's a triplet.
Triplet.
Right?
But I thought that's where the vanillic protons would be. Where
no,
you
those
just
are down. Sorry. Those are down here.
at the 6 and the 7.
Yeah.
Oh.
That's the vanillic region, right? For protons that show up that are directly bonded to carbons that are in a double bond. That's where they show up between 6 and 7.
Got it. Okay.
All right. So it's got to be, this has to be the pink set right there, right? It's a triplet. It's showing up in the right place. Actually, it's further downfield than it normally would be, because normally it would be somewhere like about 2.5. But it's possible that the presence of the double bond and that double bond being conjugated with that, you can see the conjugation here. The double bond being conjugated with the carbonyl, it may de-shield that even more and push it further downfield. So that might be why it's further down past 3. Normally that proton would show up about 2.5. All right, so that's going to be a triplet And it's at I'm gonna say 3.1 parts per million. All right, now let's look at the next set of protons, the ones that are kind of a teal color. Make sure I get the right pen. Yeah, that's it. All right, what do you think? Can't use integration because everything is integrated with 2 protons.
It's a
You
quartet.
can't-
Go ahead.
It's a quartet.
Should be a quartet, right? And compared to the pink and the green, it should be further upfield. Is that right? Because it's not next door to a sp2 carbon. Like it's not in an allylic type of position, right? So, or alpha to a proton. I mean, alpha to a carbonyl. So you can see that one should be a pentet, and it should be further upfield, right? So we got 2 choices down here, and we can see that this one is a pentet. You can see it's 5 lines, even though it's blurry up top. You can see that that's 1, 2. Zoom all the way in on that. Can you see it? That is 5 lines. 1, 2, 3, 4, 5, like that. Right. So this is a pentet. And that is at about 1.7. All right. So you have a triplet, a pentet, and then what about this one? Degrees.
Wouldn't that be a quartet?
It should be a quartet because it has 3 neighbors, right? 2 to the left, 1 to the right. So it should be a quartet, and you can see that that is indeed a quartet. That 4th line is kind of fuzzy looking, but this is 1, 2, 3, 4 lines, right? And it's at about 1.98, which is where it should be. It's allylic as opposed to being alpha to a carbonyl, which is has a little bit more of a difference in electronegativity, a bigger dipole than a simple alkyl. Simple alkene. So that's why you see it, what you see. So that's going to show up at, we said 1.9. All right, and then if you look at the proton at 6, right, it's a doublet. If we go over here on the alkene, which one of those do you think is going to be a doublet?
Would it be the one that's closest to the carbonyl group?
Yes. This one.
Yes.
So that's going to be a doublet at is it right at 6? Not 6. 6.01. I'm estimating that. All right, and then here, this purple proton, because of the multiple non-equivalents around it, it's going to split with this set of protons right here. So it's going to split with these, and it's going to split with that one. Right. So for this one, it should be a triplet, but then for this one, it should be it's going to be a doublet. So if you look at the actual signal, you can see the doublet in there, right? You see the doublet right here. Right, so you can see the doublet with a pretty good high J coupling. And then you can see the other signal kind of buried down in here. It's kind of difficult to see, but it's going to be a complex splitting pattern because of that multiple non-equivalents between the two sets of protons adjacent to it. So under normal circumstances, that would give you a triplet, and then the other one would give you a doublet. But here you can see it's more than just 5 lines. That middle signal is actually, you can't see it with this resolution, but that middle signal is actually split into 2 lines, right? So it's going to be a complex pattern in that particular case. All right. Questions? Any questions? We didn't assign them though, so let's assign them. So this is that's the gold one, and then purple is here. Notice the integration, 1 hydrogen each, so it's 2 separate signals. And then the other protons, the green we said was a triplet at 1.9. This one. And then the teal color protons we said were here. That's the wrong color. That's the same color. Now we're cooking with gas. All right. It's hard keeping track of all these colors, trying to make this make sense. All right. So in this, again, you see in this infrared, you see the carbonyl stretch, you see some alkyl stretching, you see the vinyl. I'm gonna write that in too, the vinyl stretches. Here, right? And then you also see complex splitting for the purple proton that's on the double bond, the purple vanillic proton. And then everything else is just going to follow the N+1 rule. All right, any questions about anything? All right, we only got 2 minutes left, so we're going to talk about on Wednesday the mass spec, and we're going to finish this section. So if you haven't watched the mass spec video, go ahead and watch it. And we'll pick that up on Wednesday. All right, so I'm gonna stop recording real quick.